Next, we're going to be talking about a reaction called a free radical halogenation. This is a reaction of alkanes, and as the name implies, we're going to be doing a halogenation reaction. We're going to be adding a halogen to the alkane structure. So here we have a very simple alkane, such as methane. We're reacting with chlorine, Cl2, and this reaction is going to happen in the presence of either light or heat energy. We could represent light by the symbol H nu, or heat with the symbol delta, so we can get used to seeing perhaps either of those reaction conditions. And the products we're going to get here will be CH3Cl, so chloromethane, and HCl. So you can see that we have halogenated the alkane. You replace one of the hydrogens on the alkane with a halogen. And this is a very important reaction because it's a way that we can functionalize an alkane and convert them into an alkyl halide. An alkyl halide is going to be very useful in organic synthesis. We can do lots of interesting reactions with alkyl halides. And alkanes are readily available through the distillation of our crude oil from a refinery. So we have a lot of alkanes as natural raw materials, and this would be a great reaction as a way to convert them to alkyl halides. So let's take a look at the mechanism of the free radical halogenation, and as the name implies, it's going to involve free radicals, and it's also an example of what's known as a chain reaction. And we're going to have two major steps that form the product. But before we can get to those two major steps, first we have to start the radical reaction, and that first step is called an initiation. Initiation step is one that creates radicals. And the way a radical is created in these reaction conditions is that the chlorine reacts with either the H nu or the heat, the light or the heat, and we're going to break the chlorine-chlorine bond homolytically. One electron is going to go to each side, and we're going to form two chlorine atoms. So that's going to be our very first step in the mechanism, is to create a radical. Once we have a radical started, now that radical is going to react with some other species. We'll take the chlorine and we'll react it with our alkane. What's going to happen is that chlorine is unstable, it's very reactive, and what radicals like to do is they like to pluck an atom off of another species. We call it an atom abstraction. So it's going to see this hydrogen, it's going to grab that hydrogen, one electron is going to pair up with the radical, and the other electron is going to stay behind. That's going to form a molecule of HCl, which we saw above is one of the products that we're expecting. And what else does it form? It forms a methyl radical. So this type of a radical mechanism step is called a propagation step because we're starting with one radical, and the product we get still has a radical in the product. So one radical gets converted to a new radical. We call those types of steps propagation steps. And we would describe this first step as a hydrogen atom abstraction. You abstracted or plucked off a hydrogen atom, a hydrogen with its one electrons, with its one electron. Now we have a methyl radical. What is that methyl radical going to want to do? Well, again, it's unstable. It wants to stabilize itself. It's going to look around for an atom to steal, and what it's going to find is a molecule of Cl2. So we're going to have the exactly analogous mechanism where the carbon plucks a chlorine atom off of Cl2. That leaves a radical behind. So the product we get here now has a carbon-chlorine bond. And we've just made our product. We've just formed a molecule of chloromethane. What else is formed in this step? We also form Cl dot, chlorine atom. And what can that chlorine atom do? That can continue back and attack another equivalent of the alkyl halide. Okay, so this will continue the radical mechanism. The chain reaction. So it's called a chain reaction because as soon as you form just one radical, these propagation steps will go on and on and on. These happen many times. And these are the two main steps I described in how to form your product is plucking off a hydrogen atom from the alkane, and then the resulting alkyl radical plucking off a chlorine from Cl2. We could describe the second step as a chlorine atom abstraction. So after our initiation step, all the steps of our free radical halogenation are propagation steps that are atom abstractions. Now, what else can happen in a radical reaction? Another thing that can happen are steps known as termination steps. Now, I put these separately because this is not part of the normal chain reaction that is used to form our alkyl halide. Okay, but this can also happen. A termination step is something which destroys radicals. And if you had two radicals ever combining in a step, then these two electrons could come together to form a bond. And that would, when two radicals collide, that would give a product that no longer has a radical. So this would be a way of stopping a chain reaction. Okay, now why did I put this separately? Because although it's possible to have Cl dot reacting with methyl dot, and that would be a way to possibly make the chloromethane, this is going to be a very rare reaction. Having two radicals collide is a rare reaction because any radical that you have exists in very small amounts. You have a very, very small concentration of any radical. It's a fleeting intermediate. And so what is it more likely to collide with? Is it going to collide with a stable neutral molecule that you have in high concentration, or is it randomly going to collide with some other radical that you have in a very small concentration? Okay, it's obviously going to react with a stable molecule instead. So this particular mechanism accounts for a very small amount of product. This is not how you make products. The mechanism, the propagation steps on the previous slide are the ways that you're going to do this reaction. But the fact that these termination steps occur means that it could give rise to some other side products. So for example, if we had two methyl groups, two methyl radicals reacting, that would be a way of forming a molecule of ethane. So that might be found as a very, very minor product. Very minor product, but you could see some traces of that, and that's how it might happen. Another reaction that would be a termination step is if you had some kind of inhibitor that could combine with a radical. That would form a bond and destroy a radical. So inhibitor is something that can stop a chain reaction, a radical reaction. An example of that is that oxygen gas is a diradical. The structure of oxygen, oh, sorry, I drew two bonds here. The structure of O2 actually has, rather than a double bond, has a single bond and two radicals. So oxygen is an example of a molecule that you could have in relatively high concentrations that would be a source of radicals that could scavenge some existing radicals and quench a radical reaction. So the key here is that radical reactions are run in oxygen-free atmospheres. The presence of oxygen would interfere with my radical reaction, and so we would want to do this reaction under an inert atmosphere such as nitrogen or argon or something like that. Now another thing to think about for the free radical halogenation, other than the mechanism, is the regiochemistry of the reaction. The regiochemistry is when we ask the question, which site or which region of a molecule reacts? So if we reacted, instead of using methane, let's say we use this alkane to do a free radical halogenation. If we were to do a bromination, that means we're going to replace one of these hydrogens with a bromine. We call it a monobromination reaction. Now there are 10 hydrogens in this structure. Does that mean there are 10 unique structures we can draw, monobromination structures? No, because these 3 methyl groups are all chemically equivalent. No matter which one I would react the bromine with, which of these 9 hydrogens, they would all give the same product. And then the other unique product would be if I replace this hydrogen with a bromine. So there's actually 2 possible bromination reactions, bromination products that I can get. It turns out that the major product by far is this first product, and we only get a trace, if any, of the second product. So this is a very selective reaction. We only get this product as the major product, and we can ask why this is happening. Well, it looks like this hydrogen was the one that was abstracted in our radical mechanism. Remember, we're going to be forming a Br dot, and that Br dot now is going to select a hydrogen to remove. What would be the advantage to removing this hydrogen? Well, it's on a tertiary carbon, and so it turns out that the tertiary hydrogen is the easiest to remove. If we consider the resulting radical that can form, we would have a tertiary radical if we removed that hydrogen. If we removed any of the other 9 hydrogens, we would end up with a primary radical. And remember, we talked about radical stabilities, and so we know there's a difference in those 2 stabilities. So what's going on here? This reaction we're observing is not a question of thermodynamics. This is not going to be explained by thermodynamics. It's not a question of which of these 2 products is more stable. They're both fine. They both have about the same product stability. Bromine doesn't care where it goes. The difference is a matter of kinetics. It's the path leading to the first product or the second product that varies. When we have a lower energy intermediate, when we can form a tertiary radical, that's going to give us a lower energy transition state, which is going to give us a lower energy of activation and a faster reaction. Okay? And in this case, and in many cases, the faster reaction is the one that leads to the major product. So if we look at our energy of progress or reaction diagram, we look at our starting materials, our alkane and our bromine, going to our products. And the question is, would this starting material rather go to a primary radical? Let me do this on the bottom. A tertiary radical, or would it rather go to a higher energy primary radical? The path leading to the tertiary radical is going to be a lower energy path. This energy of activation is going to be lower, and therefore it's going to be a faster reaction than if I had to go all the way up to this primary radical and down to product. That's going to be a slower reaction. So this is slower, and this is faster. So we're talking about a difference in the rates of reaction, so we describe this as a kinetic effect. The lower energy intermediate will have the lower energy transition state, and therefore will be the faster reaction. So this, again, is going to be a very common theme we see throughout organic mechanisms, is if we ever have a choice between 2 competing intermediates, it's going to be the lower energy intermediate that's favored. So because we have a vast majority of the product is this tertiary alkyl halide being formed, we describe bromination as being very selective, and the rates of reaction are orders of magnitude different. Primary going to secondary is 82 times faster, going to a tertiary center is 1,640 times faster. So with a huge difference like this, we see a huge selectivity, a significant selectivity for the more substituted hydrogen being replaced. If we look at this same reaction, but with chlorine, doing a chlorination reaction, we find that that's going to be a less selective reaction. We still find a difference, but the secondary position only reacts 2.5 times faster, and the tertiary only reacts 4 times faster. So it's very small differences in rates. So what happens is we start to see statistics playing a role in terms of how many hydrogens are available to be abstracted when we look at these major products or these product mixtures. So let's take a look at this reaction. We have this alkane reacting with chlorine NH-, so we're going to do a monochlorination. We're going to replace one hydrogen on this structure with a chlorine. And once again, we have many hydrogens, and but they're all not going to lead to unique products. Let's see if we can describe our various products here. If we called this carbon type A has hydrogens type A, reaction with any of these three hydrogens would all lead to the same chloride product. Okay, and hopefully you can see that this methyl, because you can rotate and interchange these two, this methyl is also chemically equivalent, and so would this would also give the same alkyl halide product. So we describe these two, we put that term up here, as being chemically equivalent, because they will lead to the same product if we react at either site. Okay, but if we reacted at this carbon, replace that hydrogen, that would lead to a unique product. This CH2 is unique as well, so that could be product C. And then how about this methyl? Do you think this would be the same as the first two methyls we saw? Or is this unique? Can you imagine putting a chlorine on here? Would that give you the same structure as if you put a chlorine here? Well, no, they would actually be different compounds, because here you'd have a chlorine on the first carbon and then a methyl on the carbon right next to it. Here, if you put a chlorine on this first carbon, you'd have a CH2 right next to it. So those would be different compounds. So there's actually 4 unique products that we can form here. If we draw, let me draw this as line drawings. Here's our carbon backbone. So let's call this A. See what B looks like. And C. And D. Okay, and what do these products look like? If we react with either of these two methyls, if we attach a chlorine, those would all be the same product. Now, again, we don't add a chlorine right here. There's a carbon here, so we're making a bond from that carbon to a chlorine. So that's product A. Product B is from this middle carbon. Product C is from this CH2. And product D is from this end carbon. So yeah, there are 4 unique products that we can form here. And if we look at the product ratios here, we find that we get A is formed with a 34% yield, B is 22%, C is 28%, and D is 16%. So what we get here is actually a huge mess of products. And in fact, that's what we typically see for a chlorination, is we get a mixture of all the possible monochlorination products. So we no longer have one major product like we would expect in bromination. So not only would we not be able to predict really which is the major product, but let's see if we can figure out why we have such a diverse mixture here. A is the largest proportion of any product is A. Even though it's on a primary carbon, it would have come from a primary, less stable radical. Why do we get so much A? Well, simply because there's 6 hydrogens. It's a primary radical, but there's 6 hydrogens that could be different hydrogens that could be abstracted that would all lead to product A. So this is what I'm talking about when I'm saying that statistics is starting to have a play in who's going to be your major product. Okay, and where B only has 1 hydrogen, but abstracting that leads to a tertiary radical, so that would be very stable. So that even though there's just a single hydrogen that's leading that path, it's a tertiary intermediate, so it's a very fast reaction. So that's where we're getting this balance, okay? And again, this is a secondary radical, which is pretty good, but we have only 2 of them. And this one, he's primary, and he only has 3, so that's why we get the smallest number here. So when it comes to monochlorination, your goal is typically not going to be which is the major product, because that's not something we can really tell. But this is a very nice exercise in determining chemical equivalence and being able to draw all the possible products and maybe naming them as well. It might be a nice exercise in testing your IUPAC rules. One last thing, let's just ask quickly, why would there be such a difference in the selectivity? If you know, they're both going through the same tertiary carbon radical, why would there be such a huge difference in the bromination reaction rate versus the chlorination reaction rate? And that's because, remember, we're not just forming this radical, we're breaking and forming other bonds. We're breaking, we're forming as we're abstracting this hydrogen, we're forming either a hydrogen-chlorine bond or a hydrogen-bromine bond. And the strength of those bonds is going to contribute to the overall delta H for that rate determining step. And so it turns out that for bromination, that rate determining step is more endothermic. It's a larger climb, and in those cases we see better selectivity. Finally, let's look at a case of doing an allylic halogenation. If we were to react cyclohexene with bromine and HNu, okay, we look at these reaction conditions, and we should recognize that we're forming Br dot. We're forming a bromine radical when we react bromine and light. Okay, and so we're expecting to do a halogenation reaction. We're going to take one of the hydrogens from this structure and replace it with a bromine. How many different hydrogens are there? Well, we could have this hydrogen, or one of these hydrogens, or one of these hydrogens. There's actually 3 possible products that we can draw here. Now, this hydrogen is on a double bond. That's called a vinyl hydrogen on a pi bond. And those have no reaction with halogenation reactions. Remember, free radical halogenation is a reaction of alkanes. It's for sp3 hybridized carbon, tetrahedral carbons. That's where we're going to do our atom abstraction. So we're not going to look at this position, but here we have a hydrogen and a hydrogen. This is, so let's take a look at the carbons bearing those hydrogens and see if we can imagine what the radical might look like that's going to result after atom abstraction. Okay, this carbon has 2 carbons attached, so we would describe it as secondary. And this carbon has 2 carbons attached. This is also secondary. Okay, so are those radicals equal in their stability? Well, no, because this carbon is not only secondary, it's also next to a pi bond. We have a word to describe that. We call that being allylic. And so we know that that radical would be the best one because it would have resonance stabilization compared to the other secondary radical. So we would expect as our major product that we would replace one of the allylic hydrogens with a halogen. Okay, the problem is that although we can have this free radical halogenation, bromine Br2 can also react with an alkene, a carbon-carbon double bond, in an addition reaction. So we would have a competition between the free radical halogenation and the addition. So it would be very useful if we had another source of Br dot that was not Br2. And one that is used very commonly is this structure. This is called N-bromosuccinimide, or NBS for short. And it can be used in the place of bromine. You can imagine this also being a source of Br dot, can be used to be a source of bromine radicals. The mechanism is a little more complicated than just this, but do know that if you ever see NBS as one of your reaction conditions, you can take a look at that and know that we have bromine dot. In fact, NBS typically, again, with light or heat or some way to initiate a radical reaction is really what you would see. So let's see if we can predict the product here. If we took this alkene and react with Br dot, now we would expect to do a free radical halogenation and not any other disruptive reaction where we add to the alkene. Okay, and where would we remove a hydrogen? Once again, we're going to ignore the hydrogens that are on the double bond, and we could take one of the hydrogens at either end. Okay, now this is looks like a primary radical, but it's not just a primary radical. Primary radical would be okay, but this is actually even more stable because it is resonance stabilized. And the thing to keep in mind here is because we have this resonance stabilized radical intermediate, when this now reacts with Br2 to do a bromine atom abstraction, it has two different sites at which it can react and add the bromine. So in fact, we're going to get two possible products here due to this allylic radical intermediate. We're going to get a product where the bromine has added to the N carbon, right where we had the original hydrogen, but we can also get a product where it has added to a middle carbon. Now that could have happened up here as well. This was resonance stabilized, but because it was a symmetrical molecule, that they would both lead to the same product. But in certain cases, we want to look at both resonance forms of the resonance stabilized radical intermediate and be sure that we recognize that bromination can occur at either of those sites. So for allylic bromination, we want to use NBS, and we want to draw out that allylic intermediate to see if maybe a surprise product might be formed at the same time.